right, good morning, everyone. How did the homework go? Any questions? Okay. I'm giving you a few seconds to gather your thought. All right. Okay, nobody has any questions about the homework? Did you guys have the chance to do it? Okay. Okay, can you guys hear me? You're so quiet. Can you hear me? Okay, thanks.
Yeah, we can hear you.
All right. Okay, so I will pick some problems if you guys have no questions. Usually, I get here and the questions are there. And then we move on to another idea. So yesterday we talked about the limit comparison test. So the first test, limit comparison test. Okay, and the idea of the limit comparison test is basically we have this series, we want to see whether it converges or diverges, and it's hard. So we try to compare it to something that we know its behavior. And so we have one, that's the one we have. Then we look for another one. So we will look to another one, sigma bk, that's the one we need to find. And then we look for it in a very careful way. And then we check that if at the end behavior, it means if we check if 1k goes to infinity, we check the limit. So if this limit is a nice limit, not zero or not infinity, then the only thing we can conclude with what we want, that both series either converge or diverge. So sigma ak and bk converge and diverge together. They don't tell me anything about the value of the sum. So to compute the value of the sum, once we know that it converges, we can start adding them using a computer algebra system. There are a lot of websites that can add those sums. So we just add them. So it means we add the first 100 terms, 1,000 terms, and see what they are getting close to. But once we know that it converges, we know that once those sums become close to a number, that's going to be the value. When you know it's diverge, we know it diverges. So converge or diverge together. All right. So, okay, Chris saved the day. So we're going to do the question that Chris asked. So number 11 and 14. So we start with number 11. On your quiz tomorrow or later on in your exam, when I'm asking you to show that, use the limit comparison to show if the series converge or diverge, you have to show me the way I'm doing it in class. It means all the details has to be in. So you have to compute the limit, make sure the limit is not zero, not infinity, and then make your conclusion. So not to write in converge, you have to show why it converges, why this test is applicable in your scenario. So let me look at number 11, what it is. Okay. Sigma k equal 1 to infinity of, k square minus 1 over k to the power 3 plus 4. Okay. So this is my AK. So my AK is the k square minus 1 over, that's the AK. To be able to use the limit comparison, we have to take this AK and look for a BK that behaves like AK when K is large. So our approach is, suppose K is large. Okay, what does my AK behaves like? All right, when K is large, the way we find the behavior, we say, all right, when K is large, which term basically dominate in the numerator? Because when K is large, K squared minus 1 will actually behave like K squared. That's the way we're going to do it. And when K is large, K to the power 3 plus 4 is going to behave like K to the power 3, which is 1 over K. And that would be the series I would like to compare the EK with. Okay, so that's how we choose our BK. Now, I made the choice. My choice is probably correct, but a lot of time you may do the wrong choice. It means you compare it to a series so that where the limit does not satisfy this condition. So you may do a mistake at this stage and compare AK to BK where this limit is not satisfied. It means it's not 0, it's 0 or it's infinity. In this case, your test doesn't apply. So we have to make sure that our choice is correct in the sense that the limit is not 0 and is not infinity. So we have to check that we're doing the right choice. So we have to compute the limit as L of the ratio AK over BK. So we want to make sure that they behave the same way when K is large. So this will give me the limit of K squared divided by 1 over K. Right now, the algebra and kicks in. So this will be equal to this K squared minus 1 over K to the power 3 times K over 1. I need to evaluate the limit of this expression. So this is going to be equal to the limit as K goes to infinity of K squared. I multiplied numerator, giving me that, and the denominator, which gives me this. Now this limit is obviously 1 because basically I have K cubed and K cubed, but to do it in very correct way, I divide by K to the power 3 across. This will give me that, and 1 plus 4 over K to the power 3. Now when K goes to infinity, this term here goes to 0. This term here goes to 0. The limit is equal to 1. This doesn't tell me the value of the sum or anything. Having a limit equal to 1, which is not a 0 limit and not infinity, so it's a finite limit, it means that they behave similarly. I have no idea what's their sum. If I physically add the term, I don't know what they are, but I know that those behave similarly. So now we go back and ask ourselves, my sigma BK, what it is? Does it converge or diverge? So now sigma BK, the series that I'm comparing with, sigma 1 over K. This one diverges because it's a P series with P equal to 1. Because it's a P series with P equal to 1. So remember, by the integral test, we did use this diverge. So sigma, so by the limit comparison test, the original series sigma K squared minus 1 over K cubed plus 4 also that diverges. Okay. So that's the complete treatment of this type of problem. Okay. Now let's look at number 14. Questions? Now we look at number 14. Okay. So number 14, this is my series. Number 14. Sigma one over 5 to the k plus 3. K equal 1 to infinity. Okay. And we are going to use also the limit comparison to decide whether the series converge or diverge. So in this scenario, my AK is from the general term of this series, means I'm adding terms of this form. Now I'm gonna look for the series to compare it with. All right. So when K is large, means when K takes very large value, the term of my series behaves like what? It means, what shall I compare it with? Quickly, back to you. What do you want me to compare it with? One over, exactly. When K is large, numerator is nothing. 5 to the K plus 1, when you plug in a very large value, plus 3 is like if you take 5 to the power 10 even, plus 3 is almost 5 to the power 10. We're going to compare it to that. And this will be my BK. So basically, I'm comparing the series sigma AK to sigma BK. We always compare series to something we know, something that we know its behavior. And there are two series we know their behavior, the geometric series and the P series. So we're always comparing them to something we actually know. So now I have to make sure that my comparison is working. So I go after the limit of AK over BK. Means the limit as K goes to infinity of what? Of 1 over 5 to the K plus 3 over 1 over 5 to the K. So we're computing this limit. So this would be equal to. Now, if we do a little bit of the algebra, 5 to the K over 5 to the K plus 3, all right? Now, when K goes to infinity, this limit become close to what? Okay. How shall I compute this limit?
Just divide everything by 5K.
Very nice. Divide everything by 5 to the K, because when K goes to infinity, this will go to infinity and this will go to infinity. So I really have large over large. I have to get rid of this scenario. So we divide across by 5 to the K. So divide by 5 to the K. Numerator and denominator. And this would give me 5 to the K divided by 5 to the K, it gives me a 1. 5 to the K divided by that, it's a 1. Divide this by 5 to the K. And now when K goes to infinity, 3 over 5 to the K, this will become close to 0 because 5 to the K goes to infinity and the whole thing become equal to 1. So again, our choice is very good. So my limit is a finite limit. It means basically that the limit comparison test is applicable. That's really what it means we can apply it. Okay, since the limit is a finite limit, it means the limit comparison test is applicable. Now I go to my series. The series sigma BK is sigma 1 over 5 to the K. Now back to you. Does the series converge or diverge and why? What do we know about this series? Is it convergent? Is it divergent? Back to you. Do we know the behavior of the series? Do we know the series? Oh, you guys are so quiet. Okay, why does it converge? So does the series converge, and why does it converge? That's a geometric series. So this is a typical geometric series, because if you write it up, 1/5 plus 1/5 squared plus 1/5 to the power 3, that's a typical geometric series. So that's geometric series, because every time you multiply by 1/5 with ratio equal 1/5. Since the ratio is less than 1, sigma bk converges. Hence, by the limit comparison test, our original series will converge as well. So that's the idea of comparison. We are stuck with a series. We don't know what to do with it. So we compare it to something we actually know. Any other questions? So I will take 2 problems, and I will ask you basically to give me a limit comparison before I move to another test, because they are going to be, test after test after test we're going to learn. And now my question is, what do you think I should compare it with? So suppose I take the following problem. Is of course one of the problem I assigned. Sigma 1/3 to the k minus 2 to the k. And this is problem number 24. Okay. So, and my k, I think, goes, it can start at 1 all the way to infinity. Okay. And so this is my AK. The question now is what to compare it with. Is 1/. So for k is large, right. Which series do you think I'm going to compare it with? Absolutely, I'm having 3 to the k. Again, when k is large, you're thinking, okay, which one go to infinity faster? 3 to the k dominate. So we have to compare it to that. This would be my bk. Okay, and then let us make sure we are doing the right choice. So let's see, AK over BK. So that's the limit of 1/3 to the k minus that over this. Okay. So this will give me the limit of 3 to the k over 3 to the k minus 2 to the k. All right. Now, what's this limit? Again, when k goes to infinity, this is infinity over infinity. You can apply L'Hopital's rule. If you try it, if you guys try it, you will realize that the L'Hopital rule moves us basically in a circle. It will not get me out of infinity over infinity. So what is the good way to find this limit? Back to you.
Divide everything by 3k.
Exactly. It's divide everything by 3 to the k, the dominant term. So we're going to do that because it will give me 1 divided by 3 to the k. This is 1 minus 2 to the k over 3 to the k. Okay. And now what's the limit of this expression down in the denominator? Let's say 1, 1 minus. What's the limit of that and why? 0 because. Bryce.
Because it's less than 1.
Yeah, exactly. It's less than 1. What's the it stands for?
Well, because the denominator is greater than the numerator.
No, this I will not accept.
Okay.
Because infinity over infinity is not necessarily 0.
Isn't it because 2K goes to infinity so much slower than 3K? So it's basically like 1 over 100 in a sense. So it'll always equal like something super small.
Who can give me a very, very solid reason?
Isn't it equal to 2/3 to the K
Right.
power? And then
Yeah.
that's just less than 1. So it's going to be
Yeah,
going to 0.
that's the most solid reason you guys can give me. This could be written 2/3 to the power K. Now, since 2/3 is less than 1, now the reason I sometimes object, this one goes faster because a lot of time I'm afraid I shouldn't mess up this argument. So it's not really a very, very easy argument to proceed. That's why I actually make you always give me a solid argument, because our intuition can work against us sometimes. 2/3 less than 1, it means this to the power K will go to 0. So this is going to go to 0, and this is equal to 1. And now we are actually done. Limit comparison test is applicable because my limit is not 0 and is not infinite. It's a finite limit. So I can, honest to goodness, apply it. Now, sigma 1 over 3 to the k, the series that I'm comparing it with, this one is that's the geometric series. Geometric. So it converges because the r, which is 1/3, is less than 1. Hence my original, which is my hunch was it will converge, even though it looked like nasty a little bit, but actually it also converges. We don't know it converges to what. Honestly, we don't. There is no possible way to find the sum except basically adding them. I mean, honest, the only way you know what this would get close to is you have to take a computer algebra system like MATLAB, which is some of you are familiar with, I'm sure by now, and just ask MATLAB to start adding those sums, and that's really what what they are going to get close to. So before I move on, there is one more problem. I would like also just to ask you your opinion. I don't know if I assigned it or not. Suppose I give you the following series: sigma. I'm going to put anything in here. Doesn't matter. And something like that. Okay. That's my series. And my question is, use the limit comparison. So this is really, I want you to use the limit comparison. So I'm going to let k start at 1. Whenever I put ln, I'm afraid to put ln of 1 but in this case, it works. If k is 1, 1 over 1 plus 0, it works. So the question is here, okay, I want you to use the limit comparison to decide whether the series converge or diverge. So this is my AK, and I want to compare AK to something. So when K is large, all right, what do you think will be the good comparison in this problem?
K over K squared.
K over a K squared. Absolutely correct. Why?
For the ln of K goes to ln of 100 is like 4.6, so it goes to infinity really slow.
Absolutely
And
correct.
the K squared
Perfect.
over was
Perfect. Which takes over? K squared takes over, because ln of K, as your classmate put it very, very correctly, goes to infinity very, very slow. So we've done this before in class. If you take K equal to 10, ln of 10 is very small. This is 100, and this is very small. This one will take over. So this will be my series that I would like to compare it with. So in general, actually, it's something we should really know that the ln of k is very than k. It's much smaller than k. It's really much smaller than k. So now the problem is done. I mean, once you do that, even though it looks kind of mean here and complicated, now you're done. So now if you compute the limit of the ak over bk, you're going to get the limit of, now as we've done this several times, so you will have k over k squared plus ln of k times it's going to be k over 1. So that's the limit of k squared over k squared plus ln of k. Now to compute this limit, you can apply L'Hopital's rule, or you can divide by k squared. So whichever approach, so if you apply L'Hopital's, you will have 2k over that. But now when k goes to infinity, I still have infinity over infinity. I can apply L'Hopital's rule again, and this will get me out of the infinity over infinity in this case, because the derivative of the numerator will become a 2. This will become a 2 here, so I am safe. Derivative of 1 over k is minus 1 over k squared. And this would give me equal to 1. So the limit comparison test is applicable, and I am safe to go. Because my L is a finite number. It's not 0 and it's not infinite. Not only finite, I want it to be not 0 and not infinity. Now sigma bk is the sigma 1 over k diverges. It's a p series. P equal to 1. It means my original one will diverge as well. End of the problem. Okay. All right. Today we're going to study another comparison test, which is a little bit harder than this, and it's not used a lot. It's used very little. Limit comparison is a test which we use because, as you realize, it's a really powerful test and it's very good test. We're going to see a test called comparison test, which is a little bit harder to use, but at the theoretical level, it's one of the best tests. So, but we will use it very seldom. I'm telling you that ahead of time. We will, but way less than any other test we've learned. So let me first set it up. What's the comparison test? I read it. So you guys can write, so I read it very slowly. It tells me the following. The book called it comparison. I call it ordinary. Drop ordinary in your writing. So the comparison test. It tells me the following. Suppose we have two series, sigma an and sigma bn. Okay, and both series are with positive terms. It means every an is positive and every bn is positive. And assume that an is less than bn. So every term in this series is less than the corresponding terms in bn. So what we have is the following scenario. That's what we have. So how we read this? It means A1 is less than B1. A2 less than B2. That's really what we have. And A3 less than B3. A4 less than B4. So every term in one series is less than the corresponding terms. So now I'm going to ask you the following questions. Suppose that's at a very intuitive level. Suppose when I add the B1, B2, B3, basically add them, okay, and I add those, and I get a number, whatever, I'm going to call it B. So it means this series converges. Can you conclude anything about the smaller series? Do you think the smaller will converge? Suppose if I add those, we get the larger series, it will converge. Do you think the smaller one will converge? Everything is positive. What is will be your hunch? What?
I would think so.
Yeah, the smaller one will converge. If the larger series converge, the smaller will converge. Means when we add up those terms, they cannot exceed B, because all the way B behave, the terms are positive. It means if I'm going to draw the sum, the partial sums for the B's, so suppose this is, I call Tn, the partial sum for the B's, up to Bn. This is the partial sum. So this is T1, T2, T3. They are increasing because we're adding positive terms. So those will not exceed a number. So they keep getting close to AB, the partial sums. Those trail them, but they cannot get larger than the B. So eventually they're gonna converge. So if the larger series is converging, the smaller converge. If the larger diverge, I have no idea about the smaller. So if the larger blow up, the smaller are smaller. We don't know what they behave. Now, what if the smaller series diverge? Suppose this one goes to infinity. What can you say about the larger series? Converge or diverge?
Diverge.
Yeah, if the smallest one going to go to infinity, adding the terms bigger than them will go to infinity. So that's really the content of this test. This test tells me the following. So suppose you have the following series, and every an less than bn. Then, if sigma bn, the largest is, if we add those, it converges, then the small sigma an will converge. And if sigma an diverge, then sigma bn will diverge. It means if the larger sum converges, sigma bn, then the smaller sum will converge as well. This is just to give you a visual for it. And if the smaller diverge, then the larger sum will diverge. And this series, this test hold when the terms are positive, and we will tell you why in a second, I mean very soon. That's it. The terms have to be positive. So let us apply this test. And when do we apply it? The difficulty in applying the test is that it involves an inequality, which is usually not a trivial idea, that to show that one term is strictly less than another. So let me take some example and use this test. So example number 1. Let's consider the following series. Okay. And the question is, decide whether the series converge or diverge. Let us consider the following series. Sigma, let's see, cosine square n, I'm going to divide by n to the power k over k to the power 3. K equal 1 to infinity. Okay, so it's a bizarre series. It involves a cosine term. Okay, so this is basically cosine 1, cosine square 1 over 1 plus cosine square 2 over 2 to the power 3, and so on and so forth. And so on and so forth. Okay. Now my AK here is cosine square k over k to the power 3. Now, the limit comparison test is almost hard in this case. Why the limit comparison test is hard? Why I want to see what the series converge or diverge. When I'm adding those terms, am I going to get something? Why the limit comparison test is hard in this scenario? Who can give me any reason?
Because the numerator stays the same in the limit comparisons test, and then the k third goes to infinity already. So there's really nothing close to the k to 3 that would like similar to it. So it would stay the same. The b to the k would be the same, k cosine squared k over k cubed.
Remain the same.
Yep.
Exactly. There is nothing to compare it with. I mean, when k is large, this is k cubed, fine. But cosine squared k is, what happened to cosine when k is large, actually? Can anybody know the behavior of the cosine? What's the behavior of cosine when k is large? Remember how the cosine is. The cosine by itself, without the square, is go up and down, right? So even when k is large, the cosine doesn't get close to anything. It keeps going up and down forever, oscillating between -1 and 1. Doesn't really get anywhere. Now, if you take cosine squared, it have almost the same behavior, but it's square. So it's going to be something again like this, but it will not, something like that. Always oscillate between 0 and 1, never get close to anything. So that's really what happened to it. That's almost cosine squared. It's not getting close to anything. So the behavior, we don't know what it gets close to. It's just keep oscillating. Here, the regular cosine between -1 and 1, because I square it, and this is a positive, become positive, and it oscillates between 0 and 1. So this behavior is very, very unknown. We don't know how it behaves like what. So I'm going to use, so limit comparison is absolutely out of the picture in this scenario. So we're going to use the comparison test. So how shall we use the comparison test in this case? The comparison test would require us to find something that this series is less than or bigger than. So how can I work out this problem? And why I pick cosine squared? Okay. What do we know about the cosine? Even though the cosine, we don't know what it gets close to, there is one thing we know about the cosine. The cosine is always less than 1. It's positive, and it's always less than 1. So AK is going to be always less than 1 over k to the power 3. It's going to be always less than 1 over that because the numerator is less. What this will be now, the BK, I would like to compare it with. Okay, so the way we're going to do it, that AK is always less than BK. Now, sigma BK, the sum of those, which is sigma 1 over k to the power 3, this is a P series with P bigger than 1. It means sigma pk will converge by the integral test. Hence, my original series will converge by the comparison test. By the comparison test. Okay, so that's a typical series. Whenever a series involve cosine, really, or sine, we have to go, how do I find the BK? Okay. I said that the cosine square is less than 1. Okay? So cosine square over k to the power 3 is going to be less than 1 over k to the power 3. That's how we found the BK. Hazem. Okay, that's how we found it. And that's why the difficulty of the comparison test, I need something less than. That's why it's a highly useful at the theoretical level, a little bit hard to use. But sometimes whenever the series involves cosine, we use it. Okay, but it's usually not a very easy test to use. I'm going to take another example of, again, using this test. And so example number 2. And this one, we can do it 2 ways, limit comparison, and we can use the comparison test. I'm going to do it using the comparison test now. So suppose I take this following series, sigma 1 over 2 to the n, for example, and plus n. Sorry, 2 to the k plus k. And k equal 1 to infinity. Okay, that's my series. And with that, what just did something like this. So we can use limit comparison. We can use limit comparison for limit comparison test to study the convergence of the series. Okay, but I want you to use, in this problem, the ordinary test. And let's see how to use it, okay? But we will practice basically the comparison. The comparison. So here my AK is 1 over 2 to the k plus k. Okay. Now, what is your hunch? Is this series going to converge or diverge?
Converge.
Converge.
Absolutely, because.
Oh,
Because
the BK is going to be 1 over 2K. And then
Exactly. So it's going to converge. We know because we've just done it, limit comparison test. Now, how can we use the comparison test to show that it converges? So the comparison test to show that converge, I have to make it less than something that converge. And the less has to be correct. So what shall I make it less than what and why?
Be 1 over 2 to the k.
Less than 1 over 2 to the k. Is he correct? Is this less than 1 over 2 to the k? Let us see why it is the case. Because 2 to the k plus k, the denominator here is basically larger than the denominator in this case. Means 1 over it will be less than 1 over that. So in other words, because 2 to the k plus k is larger than larger than 2 to the k. So 1 over, because then if we flip them, this would be less than 1 over 2 to the k. So that's a justification of why I can put this inequality. Okay, that's as I said, the difficulties with this test is that you have to make sure your inequality is correct. But now we're done. Now we're done. Now we can say, okay, sigma 1 over 2 to the k converges because it's a P series, sorry, because it's a geometric series with ratio equal 1/2, with R is less than 1. So the smaller series, so sigma AK, which is the smaller one, will converge by the comparison test. Okay. So sometimes we can have series, we can really do them in several ways. We can show that they converge. So in this one, I can use the limit comparison, and I can use definitely the comparison test itself because I can make this quantity less. All right. Let us see, before I ask you to give me a bunch of examples, let's see how delicate inequalities are. Suppose I ask you the following questions. Okay. My question is the following. Can comparison test the comparison test be used, can the comparison test with the series sigma 1 over 2 to the k be used to show that sigma 1 over 2 to the k minus k converges. Okay, I'll let you read the question again and think about it for a minute.
Yes.
Because
The 1 to 2k is already wait a minute. I don't think so, no.
because
Sorry, because 2k minus k is smaller than just 2k, so you can't use 1 over 2k as a bk because it's bigger than ak.
absolutely correct. So can we use it? And the idea is that show you how delicate this test is. We have to be very careful with it. And the answer is no. And that's the reason why. What your classmates said. The answer is no, because. Okay. If you take 2 to the k minus k is actually less than 2 to the k. Okay, because we're taking something away. So 1 over 2 to the k minus k, this is less than that. Okay, so the denominator is larger. It means 1 over is going to become less. So 1 over 2 to the k is less than this. Now, sigma 1 over 2 to the k converges. We know that. It does converge, but this one is bigger than it. So we cannot conclude that the larger series converges. So sigma 1 over 2k converges, but sigma 1 over 2k is less than that. So this is my AK, sorry, this is my BK, and this is my AK. Okay, so sigma 1 over 2k converges, so we can't conclude that the larger series converge.
Isn't it the other way around for the greater than less than sign?
Here?
Yeah,
No.
because isn't 2k bigger?
Yeah, 2k, but it's in the denominator. So 1 over 2k will become less, right? Think about it. 3 is less than 4. But 1/4 is less than 1/3, because that's the bigger number. You don't seem convinced.
Can we try plugging values for the k to see if that matches? Like if we plug in 2.
Okay. Do you understand this piece? I will
Yeah.
plug in. Does this make sense?
Mm-hmm.
When the denominator is larger, the fraction is smaller. Agree with me on this?
Yeah, that makes sense.
Okay. Which is larger here? 2 to the k or 2 to the k minus k? And I will plug in numbers in a minute. But I want your answer. Which is larger, this or that?
Just 2 to the k.
Yeah, because let's plug in numbers. And okay, give me any number. Suppose I take k equal to 2. Okay, I will have 1 over 2 square. And here I will have 1 over 2 square minus 2. Correct?
Yeah.
Okay, so it means 1 over 4 here. And this is 1 over, it's 4, but you're taking away something, which is 2. 1 over 4 is less than 1 over 2. You guys don't seem convinced. What's bothering you?
I understand. That makes sense.
Make sure. What's bothering you?
I got it. Just whenever I plugged it into my calculator, I forgot to put the parentheses at the bottom, so it was giving me a negative. So that's why I was confused. But then I put the parentheses, and it was all good.
Okay, all right.
Yeah.
Okay, that's really what's happening. Take k equal to 3. Again, 1 over 2 to the power 3 here. This is 1 over 2 to the power 3, but you're taking away a 3 from it. So you actually you're making it smaller. So the fraction, this is going to be larger. This is larger here. So when you flip it, it's going to become smaller. So that's 8, and that's 8 minus 3. When 8 is less than 1/5. And that's really the picture in here. Okay. So now in our situation, that's where tricky. So the smaller series converge, so we cannot conclude that the larger series converge. That's really what's happening in this scenario. So I cannot apply it. I cannot apply it, even though the limit comparison will tell me this will converge. But the comparison, we're not able to use it. That's why it is a little bit delicate to use the comparison test. Okay.
I have a question.
Yes.
So does BK have to be smaller or bigger than AK, like with just ordinary comparison?
I really I don't memorize it, which is in terms of names. The way I memorize it is like this. If the larger series converge, the smaller will converge. If the smaller diverge, the larger diverge. So now suppose you have, if I call them AK less than BK. So what you call them, it doesn't really, should not be what matters. So what's the picture? If sigma BK converge, the larger one, sigma AK will converge. If sigma AK will diverge, the smaller one, the larger will have to diverge. Okay, suppose now, because I think that's what your question, suppose I wrote them like that. Okay, I just renamed them, nothing more than this. What will be the scenario? If this sum converge, this will converge. If this will sigma BK diverge, the larger will diverge. Does this answer your question?
I think so, yeah.
Okay, so it doesn't matter what I name them. What matters is that's really the picture. That's really what's happening. You look at it, I say, okay, the largest diverge. I don't know nothing about the smaller. The larger converge, the smaller will converge. That's really the picture. Any other questions? All right, so get ready for your quiz tomorrow. There is a lot of stuff on the quiz. So I advise you to write on a piece of paper for yourself the statement of the divergence test. So on a piece of paper to help yourself, write what every test tells you, the divergence test, the integral test, limit comparison test, and the comparison test. Write them up on a piece of paper so you know how to use them correctly. Okay? All right, the class is dismissed. Anybody has any questions, you guys can stay.